Alrighty, we're gonna finish with chapter 8. Then we're gonna afterwards. We're actually gonna step backwards to chapter 7, which is more stuff about like orbits and binary star systems and stuff like that. And I wanted to skip it and go to 8 at first, partly because, well, we just did it in chapter 2, so I wanted to do something different. But I'm also going back to it because that stuff's important. It's how we determine stars' masses. And because nobody did really well on the first question on the exam, so I'm figuring, okay, well, let's get you guys solid on that. But first, let's finish up chapter, 8, about stellar spectra, all that sort of thingy. So here's stars on the HR diagram, and as the way we determine stellar masses is observing binary star systems. Okay, assume we did that. What we find is that there's a systematic trend that as you move up the main sequence, the stellar masses get higher and higher and higher. So here's 0.2 solar masses down here. Low mass main sequence stars are cool and dim. Here's the sun, 1 solar mass. Here's 2 solar masses, 5, 10, 20, even 60 solar masses. High mass main sequence stars are hot and luminous. Mass determines the location of a star along the main sequence. It's by far the most important thing. The star's chemical composition plays some role, but not nearly as much because all stars are almost entirely made of hydrogen and helium, and so details when it comes to everything else. By far the most important thing is the mass, because remember, a star is, if you will, a battle between the inward pull of gravity and the outward push of pressure. And so a star of a given mass has to generate enough pressure to hold itself up, and that sets how fast the nuclear reactions have to be going inside of its core in order for it to be in balance. And so far and away the most important thing is mass, which determines what a star's luminosity will be when it's on the main sequence. We'll see this rule gets thrown out when stars move off the main sequence because they're fusing other things in other places. It's not a tight correlation anymore. But if you're fusing hydrogen in your core so that you are a main sequence star, then where you are on the main sequence is determined almost entirely by your mass. That's a big, very important thing to understand. So I'm going to write it down. The position of a star along the main sequence is determined almost entirely by its mass. Position of a star along the main sequence is determined almost entirely by its mass. Since H fusion in its core needs to produce the right amount of pressure to support the star's weight. There's going to be a detailed pressure profile, how it varies with position within the star, but just, quick summary, has to produce the right amount of pressure. It's more complicated than just a single amount. The right amount of pressure, not too much, not too little, needed to support the weight of the layers above, and its own weight for that matter. We'll talk more about hydrostatic equilibrium soon. And that turns out to basically specify how fast the nuclear reactions are going, and if the star is going to be in equilibrium, its luminosity, how much energy it's losing every second from its surface, needs to be essentially equal to how fast it's generating energy in its core, because otherwise energy will be building up or diminishing within the star. That couldn't be equilibrium, that couldn't be balance. And so if the star is going to be in anything resembling balance, that'll need to be the case. So what we have then is the mass-luminosity relation. And I can't remember, it's been a while. Did we talk about the mass-luminosity relation in here yet? Yes, no, maybe so. Okay, good to know. I get crosstalk because I'm teaching Astronomy 111 at the same time. And so I like, wait, did I go over this in both classes or just one of them? And which one? I knew I did it in 111. I couldn't remember if I did it here. Okay, the mass-luminosity relation. That's a hyphen, not a minus sign. It's not mass minus luminosity. The mass-luminosity relation. I feel like I did mention some of this, like a star with 10 times the sun's mass is about 3,000 times more luminous. I did talk about that. And so that's what this is about, this idea that if you have a main sequence star, there's a relationship between its mass and luminosity, and that roughly speaking, if we're in the middle of the main sequence, yeah, we did talk about this. Middle of the main sequence, it's roughly that the star's luminosity divided by the sun's luminosity is approximately equal to its mass divided by the sun's mass to the power of 3.5. So in other words, you got to burn your fuel a lot frickin' faster in order to maintain the pressure needed to support your weight if you're more massive. It goes like the mass to the 3.5 power, so that if you had a star with 10 times the mass of the sun, as we mentioned, well, 10 to the 3.5 is 10 to the 3 times 10 to the 0.5, which is roughly then 1,000 times about 3, because 10 to the 0.5 square root of 10 is about 3. 3 squared is 9. So a star with 10 times the sun's mass would be 3,000 times the sun's luminosity, according to that relationship. That's not quite tracking on this plot here. I don't know. But in any case, the point is that more massive stars, as a result, live shorter lives, right? Hot young stars, like in Hollywood, live fast and die young because of the fact that they have to burn their fuel so much more rapidly, even though they've got more of it, they burn it so much more rapidly that the higher your mass, the quicker you're going to go through your life cycle, the less time you're going to spend on the main sequence before you move off of the main sequence because you've been switching to other things. What questions do you have at this point? Comments, observations? As I walk back here to zoom out so that I can use more of the blackboard as we continue our glorious discussion. Get the edge there. Zoom in a little. Okay, there we go. So we can ask, is there a lower limit to how much mass a star can have? Well, of course there is. Are you a star? I mean, the kind that fuses hydrogen within yourself? No. So something human mass ain't going to be no star. Earth's not a star. Jupiter's not a star. Jupiter has 300 times Earth's mass. How small can something be? How low can the mass be in order for something to be a star or not be a star? Answer turns out to be about 80 times the mass of Jupiter, or about 0.08 times the mass of the sun, because the sun's about 1,000 times Jupiter's mass. And so 80 Jupiter masses is about 8% the sun's mass, 0.08 the sun's mass. That's how much mass you need in order for, when you're forming as a protostar, your core to get hot enough about 10 million Kelvin, to fuse hydrogen into helium long term in your core. So there's a minimum stellar mass. Below that, degeneracy pressure, which we'll talk about later when we get to white dwarfs, degeneracy pressure kicks in before the core reaches that temperature, and degeneracy pressure, which is an inherently quantum mechanical phenomenon, can support the weight just by itself. No nuclear reactions needed. And so you have this realm, this range of masses. Turns out to be about 13 Jupiter masses to 80 Jupiter masses, where you fuse deuterium into helium for a while, but there's not a lot of deuterium, heavy hydrogen, proton plus neutron, in the nucleus for that to be sustainable long term. And then you're a brown dwarf. Below that, you're a planet. Well, I mean, we're not planets, but below that, down to some kind of arbitrary cutoff, you're a planet. But there's also a maximum mass because of the mass-luminosity relation. Eventually, the core would become so luminous that it blows off the star's outer layers because of radiation pressure. So let's summarize all that here that I've just been talking about. So the most massive stars have, well, your book says a mass of about 80 solar masses, but it's probably larger than that. Since your book was written, there's been observations of stars which seem to have more mass than that, but also such a star won't be stable. It will shed a lot of mass until it gets down to something that could be more stable. So something like 80 solar masses, probably more. Probably more, ... While the least massive stars have about 0.08 solar masses. Right, and so I just mentioned it, but we're going to talk about what sets those limits. So the lower limit is set by the need to ignite core helium burning via the proton-proton chain that fuses hydrogen into helium. And again, we'll talk about that in more detail later. And for that, you need a minimum temperature of about 10 to the 7 Kelvin. And only for masses above about 0.8 solar masses do you get there. So for the mass being less than about 0.08 solar masses, the core never reaches this temperature. Never reaches that temperature because protostars shine via gravity. They shine via the Kelvin-Helmholtz process that was mentioned on the exam and mentioned when we were talking about collapse of protostars and so forth, virial theorem and all that. Kelvin-Helmholtz process is how protostars shine, and so as they contract, they're converting gravitational potential energy into radiation and thermal energy within the cloud. And if you're below about 0.08 solar masses, that thermal energy that gets produced within the cloud from gravitational potential energy as it contracts never gets the core's temperature up to 10 million Kelvin, and so you never ignite the proton-proton chain. And we define a star to be something that has sustained nuclear fusion within it. And so with that definition, these things are not stars if you're below that. Questions, comments, observations? So then the upper limit is what's called the Eddington limit. After, in another great name from the past, Arthur Stanley Eddington, that's a great name, Arthur Stanley Eddington, famous astrophysicist who deduced this limit, the upper limit, is set by the Eddington limit. We'll meet Eddington more times than once as we talk about stellar astrophysics. Since L goes like about m to the 3.5, it's even steeper at the upper end of the main sequence, right? Because that, well, it's not right, but it turns out that it goes even faster than that at the upper end. Related to the main sequence, it kind of tails up and tails down at the end. It's kind of a sigmoid instead of a straight line on the diagram. So it's kind of hinted at by that. It's even steeper at the upper end of the main sequence. The upper end of the main sequence. The radiation pressure, and again, we'll talk more about radiation pressure later, but the idea is, remember that photons don't just carry energy, they carry momentum as well. The energy of a photon is its momentum times the speed of light in unnatural SI units. And so if you have photons flowing through a star, they contribute pressure in addition to the ordinary kind of gas pressure. And if there's enough luminosity, if there's enough photons flooding outwards from the core due to the nuclear reactions, that radiation pressure can actually be even more important than the gas pressure is in extreme cases, such that the outer layers of the star, which are further away from the center and thus weakly held by gravity, can be blown off by radiation pressure. And so that sets the upper limit. If you tried to make something 1,000 times the mass of the sun, it would have to fuse hydrogen so rapidly that that flood of photons would just blow the weakly held by gravity outer layers into space. So the radiation pressure is so large that it exceeds gravity in the outer layers. If you go beyond about 80 or so solar masses, so a star more massive than this will suffer rapid mass loss until it's below the Eddington limit. Have a very strong, what we call stellar wind, blowing its outer layers into space until it's below the Eddington limit. So the main sequence doesn't keep going on and on forever in both directions. There's a lower limit and an upper limit set by those conditions. Currently entertaining questions or comments or observations? Okay, I'll just stand here waiting for people to catch up with their writing. Can I say the next thing? No, I can't. Max is still writing. Max is still writing. Max. Both Max are still writing. Yeah. I mean, if I cross my eyes, there's two of you. All right. So, now I want to talk about how, so we've talked about giants and supergiants and all that sort of thing. Why, if the star's, excuse me, much more luminous than a main sequence star of the same temperature, it must be a lot larger, blah, blah, blah. And if we can measure a star's distance via parallax and its apparent brightness, we can actually figure out what its luminosity is, and that would tell us to plot it way high up on the HR diagram. But many stars, and this is becoming kind of less of a problem with the Gaia satellite, which is getting all kinds of parallaxes for stars much further away than we could before. But even still, even with that consideration, for many stars, the way we know whether it's a giant or not is not by knowing its distance, because it may be too far away for us to get its distance by parallax, or at least traditionally before we had Gaia around. And even Gaia, there's errors associated with the parallaxes. It does better in some places in the sky than others, and so forth. And so it turns out that what we would normally do to classify stars according to their luminosity is look at their spectral lines. And what we find is that a supergiant star like Rigel, anybody know what constellation Rigel's in? Same one that Betelgeuse is in. Anybody know what Betelgeuse is in? Yeah, Orion, yeah. Betelgeuse and Rigel are on opposite sides of the belt in Orion. So one's at upper left, that's Betelgeuse, one's at lower right, that's Rigel. Rigel is a blue star, spectral class B8. Its luminosity is about 58,000 times the sun's luminosity. Then we have the main sequence B8 star Algol, the demon star, whose brightness noticeably varies. Luminosities, it's a dim bulb, only 100 times the sun's luminosity. Here's the thing, look at their spectra. They're both B8. And so that means that they should have very similar spectra to one another. But what you can see here is that the spectral lines in Rigel are notably narrower in wavelength range than for Algol. And it's the broadness or narrowness of the spectral lines which gives us our first blush at how luminous a star is. It's very tightly correlated to how luminous the star is, or at least it's pretty tightly correlated. So let's explain how that works. And it's going to involve a little bit of quantum mechanics, not in great detail, but so you all know about the uncertainty principle in terms of the uncertainty in the position times the uncertainty in the momentum, which have technical definitions in terms of the standard deviation, blah, blah, blah. The delta x, delta p is greater than or equal to h bar over 2, right? You've heard that. Have you heard about the energy-time uncertainty principle? So there's also an energy-time uncertainty principle which says that the uncertainty in a quantum state's energy multiplied by the uncertainty, well, kind of by its lifetime, because excited states tend to decay. We say that delta E, delta T, where delta T is a measure of the state's lifetime, that also works out to be greater than or equal to about h bar over 2. So when we talked about the formation of spectral lines, again, I'm cross-talking myself here. We talked about spectral lines, right? Yeah, okay, yeah, of course we did. We wouldn't be doing this if we hadn't done that first. Hi. Okay, so anyway, hello, audience at home, would you like to see this figure that I'm showing here? I'll bet you would. Let me turn it over there. Oh, look at that. Look at those narrow spectral lines for Rigel and those broader spectral lines for algol. We made it sound like, well, the energy of n equals 2 is some specific value, right? We said bunch of constants over n squared is the energies of the levels in hydrogen. And then we made it sound like that was a perfectly well-defined energy, and the photon, in order to make a transition from n equals 1 to n equal 2, it would have to have the difference in energies between those two levels in order to cause the transition. But that's not quite right. So first of all, if it had if those energies were exactly precisely defined, there would be zero chance of a photon having exactly precisely that energy to cause the transition. So in reality, the energy levels have some spread in them. There's a bit of uncertainty in the energy levels. And furthermore, a photon, unless it occupies the entire universe and has existed forever, actually it too doesn't really have an exactly precise energy. And so that's why we can actually get atomic transitions, is because it's a matter of, well, the electrons don't have exact energy levels, and so the photon transitions don't have exact values of the energy they need. They just have, well, it should be very close to this particular energy. And the photon itself doesn't have an exact energy. It's just got, well, it's got the highest probability of being observed to have this particular energy, but there's a spread around that. And that comes under this energy-time uncertainty principle. If a state isn't going to live forever, it doesn't have an exact energy, it turns out, in quantum mechanics. And so while the ground state could live forever and has a nice sharp energy, higher level states, which will spontaneously decay to the ground state, have some uncertainty in their energies. That's kind of the qualitative picture here. And what we're going to argue is that the energies are more sharply defined for supergiants than they are for main sequence stars. They're more sharply defined for supergiants than they are for red giants, for stars that aren't, for giants that aren't supergiants. And it has to do with the density of the atmosphere, because collisions between atoms can cause them to undergo transitions down to other levels. In other words, we know that if an hydrogen has its electron in n equals 2, it will spontaneously drop down to the ground state. If you just had it there by itself, after a little bit of time, it will drop down to the ground state. How much time? Well, that's probabilistically determined. You can't predict when any given hydrogen atom will decay. You can only talk probabilistically. What's the decay probability per unit time? But what we haven't mentioned yet is that a collision between atoms, where one of them is in, say, n equals 2, that collision can also cause the electron to transition to another state, either upwards or downwards. And those collisions effectively then are shortening the lifetime. They're making them undergo transitions quicker than they would without the collisions. And on top of that, and I'm saying a lot before I start writing it down, just okay. On top of that, have you heard of like van der Waals forces before? So that's where an atom or a molecule, even if it's got the same number of electrons as it does protons, there are residual electric fields. The electric field beyond it isn't exactly zero. So if you bring atoms close to one another, they feel one another's residual electric fields, and that shifts the energy levels. Because remember that the energy levels of the electron in hydrogen are due to its interaction with the positive charge of the proton. If another hydrogen comes along, it's feeling a different electric field because it's feeling not just the electric field of its proton, but also of the other atom, and that shifts the energy levels as well. And you can imagine that they're shifting in a time-dependent way as the particles, as the atoms move close to one another. So if you have a bunch of hydrogen atoms in a gas, there's a spread in their energy levels just because they're feeling one another's electric fields. All these things put together, the stronger these effects are, the broader the energy levels are. There's a greater range, if you will, of energy levels of the different atoms because they're each in a somewhat different environment. And the bigger the spread in energy levels, the broader the spectral lines will be. That's the big picture. The bigger the spread in the energy levels, the broader the spectral lines will be. And I'll write this down too, but I'm just kind of, I want to say it first as opposed to very slowly writing it. I think it would be helpful to say it all first faster, then take our time and write it down. And the idea is that in a denser atmosphere, this effect will be bigger. There will be more spread in the energy levels in a denser atmosphere where there's more collisions, more close encounters of atoms with one another than in an extended low density atmosphere where there's a greater amount of isolation of the atoms from one another. They're further apart on average, so they don't collide as often, they don't come close to one another as often. Well, it's going to be in a supergiant star with a really extended, spread out atmosphere that you get that the atoms are lonelier and therefore have more sharply defined energy levels and therefore have narrower spectral lines compared to a denser main sequence star where the atoms are not as lonely. They get together more and it spreads the energy levels out more. So that's kind of the big qualitative picture. And then we'll write this down. So what questions do you have at this point? Let's write it down then, shall we? All right, let me get the camera over to where our audience at home can see what I'm pointed at. Hello, audience at home. Gotta scare them every once in a while, right? It's like, oh my God, what is that? Oh, it's just Dr. Harmon. Well, that's scary. Okay, so if my wife were here, she'd be going like, yeah, that would scare me or something like that. But so. Then again, we might be known to make faces at each other, so it's Halloween, right? So there should be like scary things happening, right? Yeah, it's not set up yet. You gotta check out the new candy bowl that my wife found at Target for Halloween. So you have to stop by sometime and enjoy what happens with it. But we have to find candy first. We gotta go buy candy. So. All right, so let's write all this out, because if you can't find the parallax of the star, it turns out that you can look how broad or narrow spectral lines are and classify it into different what we call luminosity classes. You can estimate how luminous it is based on that, because it lets you see, why is that a giant? Is it a supergiant? And so on and so forth. So, careful examination of the spectra of dwarfs and giants of the same spectral type. And remember, dwarf just means main sequence. Russell called main sequence stars dwarfs. Careful examination of the spectra of dwarfs equals main sequence stars, just as a reminder, and giants of the same spectral type, so the overall same kind of ratios of line strengths, because remember, that's how we classify them. How strong are the hydrogen lines? How strong are the singly ionized calcium lines? And so on and so forth. Dwarfs and giants of the same spectral type reveals that giants have narrow spectral lines. And supergiants have even narrower spectral lines. And supergiants, I have to say, I really, there's one thing I approve of, is that they decided to say supergiants, right? I mean, that's like nice. Supergiants have even narrower lines. So here's, I'll attempt to summarize all that stuff I was talking about here, and I hope all that stuff soaked in enough that this will make sense. This is because in the lower density atmospheres of giants, because really the masses aren't so different, it's just that it's spread out more in giants and supergiants. In the lower density atmospheres of giants, close encounters, all right, this isn't going to work, but I'll try. Well, that was terrible. Yeah, did you get the reference there? Yeah, okay. Close encounters, what's it? I said it's a movie reference, yeah. Oh, you never seen it? Oh, did you get the reference at all? Or is it, oh, okay, we need to fix that sometime then, yeah. Classic 77, came out same year as Star Wars. Yeah. What's that? Spielberg. Yeah, Spielberg. Yep. Yeah, so Spielberg put that out, and George Lucas put out Star Wars, both in the same year. Yep. Close encounters between atoms which shift energy levels via electric field interactions. And collisions which can induce transitions and thus shorten the lifetimes of states I'll make it quantum states, got to make it fancy, of quantum states. And since it's Halloween, if you say quantum, right, it's got to be, right, it's got to be spooky, right, because it's spooky quantum stuff, right? And thus shorten the lifetimes of states. Where was I? Because I'm not quite writing quite. This is because in the lower density atmospheres of giants, close encounters of atoms, which shift energy levels via electric field interactions, and collisions, which can induce transitions and thus shorten the lifetimes of quantum states, are less frequent than in the denser air atmospheres of main sequence stars. I'll let y'all catch up with that before I start writing the other stuff. Okay, I feel like people are caught up. Maybe, I don't know. All right, and so then, what do I want to say here? From the energy time uncertainty principle delta E delta T is on the order of h bar. I'm not going to even bother with the h bar over 2. The energies are more the orbital, I'll say, orbital energies are more precisely defined for the giants, and thus the spectral lines are narrower. The photons have to have a more precisely defined energy in order to make those transitions. The orbital energies are more precisely defined. There's lower uncertainty in them. So the needed photon energies to cause transitions are as well. And leads to, therefore, narrower spectral lines. And this all falls under, I don't think I say that in the notes here, but this all falls under, quote unquote, pressure broadening. Because the idea is, well, the density is related to the pressure, and so the higher the pressure in the atmosphere, the broader the spectral lines will be. So this gets called pressure broadening. It also gets called collisional broadening. And on some level, pressure broadening is about the close encounters, and collisional broadening is about the collision. So I think I'll say that. Pressure broadening for the close encounters and collisional broadening but if you've got one, you got the other. So sometimes they'll just say pressure broadening to encompass it all. Pressure broadening for the, do I need to say it, question mark. For the collisions, obviously. And so anti-jump cannon, awesome name, came up with the modern version of the spectral sequence in terms of OBAF Gookham and the subcategories of, like, you know, G1, G2, G3, G4, G5, and so forth. The sun is what spectral class? G2, yes, the sun is G2. And then this idea was used to further refine it so that we now also attach a Roman numeral to the spectral class called its luminosity class, and Roman numeral 5 stands for main sequence star. So that means, and I'll say more about this in a moment, the sun is not just G2, it's G2 Roman numeral 5. Whereas a red giant would be G2 Roman numeral 3, a subgiant's G2 Roman numeral 4, and so on and so forth. And that's based on the broadness or narrowness of the spectral lines. And this was first set forth by William W. Morgan and Philip C. Kinnan, who were at Yerkes Observatory in Chicago. Now, Phil Kinnan later was at Ohio State, and he, after he was retired, liked to hang out at Perkins Observatory. And he died just before I came here. So there's a photo of Phil Kinnan puttering around in the garden of Perkins Observatory, along with his hat and sweater. So when you go to Perkins Observatory, I will have you touch his hat and sweater, and you'll have touched the hat and sweater of Phil Kinnan, who is one of the Ks in the MKK spectral sequence definitions. So you'll be touching greatness there. I didn't get to meet him, unfortunately, because I think he died in 98, and I came in 99. But I did know, like, students who, I knew a student who, you know, she had worked the summer at Perkins, and she talked to him, and he was apparently a lovely man. It was all very nice and so forth. Well, the other K is Edith Kellman, who printed the photographs of the spectra in the catalog, and they gave her credit for it as well. So MKK Spectral Atlas we'll talk about, the Atlas of Stellar Spectra, is Morgan Kinnan Kellman. And that's where we stand in terms of spectral types of stars. So let's write all this glory here. Dates back to 1943. 1943, William W. Morgan and Philip C. Kinnan of Yerkes Observatory, home of the world's largest refractor, then operated by the University of Chicago, my graduate alma mater. That's in Wisconsin, in Lake Geneva. Of Yerkes Observatory published the Atlas of Stellar Spectra, an absolute classic. The Atlas of Stellar Spectra. Setting the standard for spectral classification. Consisting of photographic prints of 55 stellar spectra of various temperatures and luminosities. Which I'll abbreviate as T and L. You'll know T is temperature and L is luminosity, right? Various T and L. And in addition to the title Atlas of Stellar Spectra, astronomers often refer to it as the MKK Atlas. Where the second K stands for Edith Kellman. Who printed the spectra and is listed as a co-author. And after the break, we'll say more about the MKK Atlas and luminosity classes and all that good stuff. And that'll be this chapter. All right, so the point here is, as I was hinting. We get these Roman numerals attached to the spectral classes. And so we have the MK, two-dimensional MK spectral classification system, where one dimension is spectral type and the other is so-called luminosity class, which basically tells you what Roman numeral you attach to it based on calibration with stars, where you can actually measure their distances from parallax or via what's called the moving cluster method, and determine their luminosities. Allows you to say, oh, well, they're in one of these other stripes, if you will, on the HR diagram. And I've noticed there's a lot of spread around them. But in other words, you can roughly estimate the star's luminosity from its spectral lines. They're subdivided into class 5, not shown here, Roman numeral 5, which are the main sequence stars. Somewhat narrower lines is subgiants class 4. Yet narrower is giants class 3, luminosity class 3. And then there's 1B, 1A, and we'll see there's also like a 1A0 with entertaining names here, which we'll write out. And so this is appended to anti-jump cannon's so-called Harvard spectral type. That's the G2, B4, all that business. So let's write all this out, shall we? The MKK atlas established the two-dimensional Morgan-Canaan MK spectral classification system. The MKK atlas, that classic 1943 publication, established the two-dimensional Morgan-Canaan M-K spectral classification system. In which a luminosity class designated by a Roman numeral, because other classes already have Arabic numerals. You see that, by the way, sometimes they'll do like a poll. They'll ask people, do you think we should teach Arabic numerals in American schools? And a lot of people are like, no, you should not teach Arabic numerals in American schools. Okay, then I guess we'll stop writing 0, 1, 2, 3, 4. Anyway, designated by a Roman numeral, is appended to any jump cannon's Harvard spectral class. So the G2, B4, all that, that's called the Harvard spectral class. Well, I guess you have to say the Harvard spectral class, something like that. Harvard spectral class. And so here's one illustration of it there, but I'm going to draw a figure where I kind of qualitatively sketch it out and include all of the very entertaining names for the different luminosity classes. So again, the idea is that if you've already calibrated this with stars where you can measure their distances and apparent brightnesses and then get their luminosities, well, this allows you to take a star where it's too far away for parallax, but you look at its spectrum and the narrowness of the lines, you base that and you say, oh, well, that's spectral class luminosity class 3, why that's a giant star of this spectral type, and you get some notion of what its luminosity is. And then from that and its apparent brightness, you can get an estimate of its distance. And before Gaia came along, that was how most stellar distances were estimated, actually, for stars that are too far away for parallax. Now Gaia is kind of fixing that by being able to see parallaxes for a much larger number of stars, which is super important, because as you might imagine, there's quite a bit of uncertainty associated with determining the luminosity this way. And you can see, look how much spread there is amongst the giants, right? So just knowing its luminosity class 3 doesn't tell you exactly what its luminosity is. There's an intrinsic spread there. Not only that, there's an uncertainty in, well, let's see, the lines are narrow, you know, okay, it's 3, but, and so how big is it, etc. But still, if you can look at the spectrum and say, it's a K5 Roman numeral 3 star, well, you know, it's about this luminosity, and from its apparent brightness, you could estimate what its distance is. And that's called spectroscopic parallax, which is, in the tradition of astronomy, a terrible name, because you're not measuring an angle, right? Parallaxes are angles. But you are estimating what its distance is, and the distance would tell you the parallax. And so instead of calling it its spectroscopic distance, which I would have done, no, let's call it spectroscopic parallax. Funny name, but anyway, it's really a distance estimate. So here is a sketch of kind of the different luminosity classes. So here is effective temperature. Which way am I going to draw the arrow on this axis to indicate the direction of increase? Yeah, because we're astronomers. And then here is luminosity. Which way I draw the arrow? Up. Yeah, weirdly enough, we let luminosity increase upward on our plot. So now let's kind of sketch where the different luminosity classes are, sort of qualitatively here. So we got our, that's the main sequence. That's luminosity class 5. Below that, although as we'll see, really kind of to the left of that is luminosity class Roman numeral 6. And then over here, we've got D or WD, because these are what suckers down here in this part of the diagram. Those are white dwarfs down there. Yeah, you got your WDs. Makes me think of like engine lubricant, right? WD-40 and that kind of thing, right? Or whatever, or just lubricant in general. Anyway, and then we've got kind of here's luminosity class Roman numeral 4, and luminosity class Roman numeral 3, and 2, and 1 sub B, and 1 sub A, and 1A0, and 1A-0 is, according to your book, these would be the extreme luminous supergiants. But I think, I haven't seen this officially confirmed anywhere, but I think that people have adopted another name for these now that you hear more commonly, because I've definitely seen this commonly, and I suspect it's supposed to apply to what would have been before called extremely luminous supergiants, and that is hypergiants. I'm going to put a question mark there because, like I say, I see hypergiants referred to, and I think it's referring specifically to that luminosity class, but I'm not sure. Maybe it also includes 1A. Why 1A? Those are the luminous supergiants. I mean, when we say luminous, we mean luminous here, right? In other words, like 1A on this is showing like 100,000 times the sun's luminosity, and above that, you know, close to like 1,000,000 times the sun's luminosity. Such stars are very rare, but they give off a lot of light. In our galaxies, we'll see in other spiral galaxies, in visible wavelengths, spiral galaxies like ours look blue because of O and B type stars, largely main sequence O-B type stars with smattering of B supergiants and O supergiants and stuff like that. They make up a tiny fraction of the stars, but each one is so luminous that they dominate photographs, even though they're like squeaky wheels, or like, you know, imagine a population where there's just a few people that are like screaming at the top of their lungs all the time, and so those are the ones you hear, and everybody else is a lot quieter. Anyway, you got 1A as your luminous supergiants, and then in a bit of inspiration here, I guess not really sub-B, I think it is just 1B with not a subscript. I think it's not, I actually don't remember. Anyway, why these would be less luminous supergiants. Still luminous, but less luminous supergiants. And then you got 2, why those are bright giants. I mean, giants are already bright, come on, but these are bright giants, just to distinguish them from plain old giants, which again, they're bright, but let's call the really bright ones bright giants. And these guys, why these are normal giants. If something rare can be normal, those are normal giants. Those are your run-of-the-mill giants. And then we got, oh, I guess have to be consistent here. Yeah, okay. Sometimes with Roman numerals you put little crossbars and sometimes you don't, so I guess I'll put crossbars and everything. You can decide if you want to or not. So yeah, so 2 is the bright giants, 3 is the normal giants, 4 are so-called subgiants. The sun will be a subgiant as it is switching to fusion of hydrogen in a shell surrounding the core, which go faster and faster and faster, and so the sun will, on the HR diagram, as we'll see, quote-unquote, climb the red giant branch, start as a subgiant right after it leaves the main sequence, and move up the red giant branch to become a normal giant. And then 5, that's your main sequence, i.e. dwarf stars. Dwarf stars. So the sun is G2 Roman numeral 5, which is often called then a G2 dwarf. You might see the sun described as a G2 dwarf, where again, dwarf doesn't really mean that it's small, except compared to giants. It's just, it's a main sequence star. Luminosity class 6 is what we call subdwarfs. They're also main sequence stars, and at first it was a bit of mystery as to why you can actually tease out another group of stars that are parallel to the main sequence there. They're really main sequence stars too. As we'll see, the difference is that these are older main sequence stars that therefore have less metallicity, less heavy elements in them, because, let's see, hydrogen and helium came out of the Big Bang. What about everybody else? Pretty much made in stars after the Big Bang. So very old stars, the universe was younger then. Not as much, not hydrogen and not helium had been made. Those stars have lower abundances of heavy elements, of what astronomers call metals. And as we'll see, that makes their atmospheres more transparent, because they don't have as much H- ion in them. They're more transparent, which means we can see deeper into them where it's hotter. And so a subdwarf that has the same luminosity as the sun will have a higher surface temperature because the surface lies lower down. You can see deeper into the star because it is less opaque, the outer layers. So in other words, it shifts a bit to the left towards higher surface temperature compared to the sun. So again, we'll talk all about that later, but the subdwarfs are low metallicity, very old main sequence stars that have systematically higher surface temperatures than a solar metallicity star of the same surface temperature on the main sequence. And so it's distinctive enough that they show up as another subclass. And then the WDs, those are the white dwarfs. Sometimes it's just called D, but I'm going to say WD. Those are the white dwarfs. And so that's kind of the summary of stellar classification right there. That's, pick any reasonably normal star, and it'll show up as G23, B84, things like that. Well, 4 doesn't go up that high, but, B81 or something like that, et cetera, Roman numeral. So what questions do you have? Stellar. All right. So, should mention what I said before, which is that at least before the Gaia satellite, which was pre your book, post your book. So your book, there was no Gaia satellite yet. There'd been Hipparcos, but Gaia is measuring many more parallaxes, at least before the Gaia satellite greatly expanded the number of stars for which we have parallaxes. Because it's in space above the atmosphere, so it can do much more precise measurements. So now I don't actually know what fraction we get from spectroscopic parallax versus Gaia, but I suspect it's tipped now towards Gaia, like most distances would be from Gaia. Most stellar distances came from using the spectrum, the spectral line widths, to assign a luminosity class. And thus, an approximate luminosity so I'll point out needed calibration from nearby stars. Of course, there's no such thing as a star that's truly nearby, but you know what I mean. Nearby compared to much further away ones. Needed calibration from nearby stars where you can actually find parallaxes. Nearby stars with measurable parallaxes. And that's the point, is that Gaia has greatly expanded how far away we can measure parallaxes. It goes out to thousands of light years now, whereas that wasn't true before, with measurable parallaxes. Okay, now read it again because it's getting long enough, I don't remember. At least before the Gaia satellite greatly expanded the number of stars with measured parallaxes, most stellar distances came from using the spectral line width, not just one, line widths to assign a luminosity class, and thus an approximate luminosity. Well, that needed calibration from nearby stars with measurable parallaxes. And then using its measured magnitude, apparent magnitude, measured apparent magnitude, right? That was the little m. And for the luminosity, what tells us that what do we call the magnitude measure of luminosity? Why, that's the stars as opposed to its apparent magnitude. It's another A word. It's magnitude. Yeah, it's absolute magnitude. So I'll add up here, sorry. And thus capital M, the absolute magnitude. Right, because notice, right, the other way you can put the axis is absolute magnitude. So the luminosity class gives you an estimate of the star's absolute magnitude. We can measure its apparent magnitude. Finding D from the magnitude distance relation, right? The one that says, what is it? D is 10 to the, oh crap, I think it's what, well, I'll just write it. From little m minus big M is 5 log D minus 5, right? 5 log D minus 5. And then you solve for the distance. So it's really like 10 to the 0.4, blah, 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 but I don't remember that, so I'm just going to put that. Because that's implicitly telling you how to get the distance. So in other words, the magnitude distance relation. Right, so you get the picture is you can, from the spectrum, you can both figure out what its spectral type is. If you're an expert, you can look at the line strengths and say, oh, this is spectral type K4. And then from the narrowness of the lines, you could say, not only is it K4, it's luminosity class 3, so it's a K4 3 star. Oh, it's K4 3. Why, that means it's about here on the HR diagram. Why, that means its absolute magnitude is about -1. And if I measure its apparent magnitude and get that that's +6, let's say, I can plug into this formula right here to estimate the distance using the, basically remember that the magnitude distance relation is the what law in terms of magnitudes. The magnitude distance relation fundamentally comes from the for light.
Inverse square law?
The inverse square law, yeah, really you're using the inverse square law. The written in terms of magnitudes. So that's what we're really fundamentally doing. We're using the inverse square law to figure that out. Inverse square law. That's really the inverse square law that we're using right there. That's the inverse square law. Don't you forget it. Oh, I had it here. Okay. It's in my notes, dummy. So it's D equals 10 to the power of little m minus big M plus 5 over 5, which I could have solved, but I was scared, you know, because doing things in front of people, you can mess up, right? So that's what you'd really do. It's just you'd plug your measured little m and your estimated big M from the spectrum into this formula right here to get the distance in parsecs. And that is called the spectroscopic parallax. Because if you had the distance in parsecs and for some reason you wanted to say what its parallax is, why, what would you do? What's the relation between distance and parallax? If the distance is in parsecs and the parallax is in arc seconds, how are those two related to one another? D equals, do you remember? Yeah, the 1 over P, right. D is 1 over P or P is 1 over D, right? That's the, if you put distance in parsecs, parallax in arc seconds, D is 1 over P, P is 1 over D. So once you had D, if for some weird reason you wanted to express it as a parallax, you'd take that reciprocal of the D in parsecs and you'd say, well, that's the parallax. Except who cares? What we really want is the distance of the star. But whatever. Who knows who comes up with these things? Okay? Questions? Okay, I hope it's a lack of questions, meaning, no, this is so clear, there's nothing I could possibly ask a question about, as opposed to, what the hell are you talking about, right? So remember, you're supposed to say it if it's, what the hell are you talking about? Or maybe, what the hacky dang thing are you talking about? Gee whiz, Dr. Harmon, you know, something like that, because this is, of course, a family-friendly astrophysics class, right? Anyway, all right? So, yeah. And I will just mention a couple more things here. I don't remember if the camera's, I think the camera's still zoomed in here. Is anybody still writing this stuff out? Because it's pointed forward, but I think I've still got it zoomed into here, so. I'm gonna erase it, it's gonna go, ah! Oh no, ah! It's Halloween. I wish I had some way of, like, when I was doing this, like, all of a sudden, like, you know, red liquid would start dripping down the board, right? You know, I massacred the writing. It's, imagine that's happening right now. Yeah, maybe I can put that in post in the video. No, I can't. That's going to be too much effort. Anyway, it'd be cool, though, wouldn't it? Anyway, I guess I should mention for completeness here, there is an intrinsic scatter of about plus or minus a magnitude for each luminosity class, which makes the distances determined by that uncertain by a factor of about 1.6, so it ain't great. There is an intrinsic, like it belongs to the stars themselves, because, you know, luminosity class 3 just says it's a giant, but giants keep changing their radius as they climb the red giant branch in the HR diagram. So it's not super precise. There's an intrinsic scatter about a magnitude, either way, about plus minus 1 magnitude for each luminosity class. Making D uncertain. The distance is determined this way, uncertain, by a factor of about 10 to the 1 magnitude over that 5 that shows up in the formula for D equals 1.6. Well, this is why Gaia is so important. So in particular, not only is it important for determining stellar parameters, but also it's cosmologically important, because you may know, if you've had cosmology, and you will know by the time we're done with 311, that there's a very important class of stars called Cepheid variables, where there's a distinct relationship between how long they take to pulsate and what their luminosities are. Somebody should do a senior project on them. And so they're also generally far enough away that before Gaia came along, we couldn't measure their parallaxes reliably. So that means it's harder to determine exactly what is the relationship between their luminosities and their periods, and they're so luminous we can see them in other galaxies and use them to figure out how far away those galaxies are and determine things like the Hubble constant, how fast the universe is expanding. So Gaia getting parallaxes, good, honest-to-goodness parallaxes of Cepheid variables helps calibrate that period luminosity relation, which is super crucial in determining the Hubble constant, for example. So stellar parallaxes, it's very important. Stellar distance is very important. Beyond just understanding stars better, it's important to understand them for their own sake as well. For the sake of for the sake of cosmology and so forth as well. before basically said, not only is it important to understand them for their own sake, it's also important to understand them for their own sake as well. I am fully zoomed out here, so I can use the rest of the board to say one more glorious thing that is good to keep in mind about stars. And that is that in general, as you go up the main sequence, the stars are becoming more massive, and they're also becoming less dense. Higher mass stars on the main sequence have lower average densities than lower mass stars do. So their volume is bigger enough to more than make up for their extra mass. They are less dense. And this has consequences. For example, this extends all the way to their cores. So when a low mass star like the sun first starts fusing hydrogen into helium, first starts fusing helium into carbon in its core, it will do so explosively because the core will be high enough density that it will be what we say degenerate again. There's that degeneracy pressure we haven't talked about yet. And so you get the helium flash, because I have to say because of Flash Gordon. Whereas high mass stars don't have a helium flash because their cores are lower density, not dense enough to be degenerate when the helium burning begins, and so they smoothly begin fusing helium into carbon. They don't have a helium flash. So for them, it's like, for them, there's no helium flash, right, in that case. So, all right, got to distinguish, right? That's important. But let's just talk about the average densities. So I'm not going to go through it, but I'll just mention the results because you'll be fascinated enough to do it on your own time. Example 8.2.1 shows that stellar average densities decrease as we move towards earlier spectral types. And remember, that's that funny terminology where earlier means towards the left, towards O. So O is the earliest spectral type, M is the latest spectral type, because of the discredited, well, that's basically just wrong, old notion of stellar evolution where stars started out hot and energetic O stars, and then they just kind of lost steam and turned into cool M stars. So the O stars were early, and the M stars were late, decrepit stars. And now we know that's not true anymore. Once a star hits the main sequence, it hardly moves at all until it moves off the main sequence, becoming a subgiant and then a giant. Or if you're a very high mass star, you just go straight into being supergiant, part of the diagram. Anyway, example 8.2.1 shows that stellar average densities decrease as we move towards earlier spectral types. On the main sequence. Well, even for, well, like Betelgeuse. Well, we'll get to Betelgeuse in a minute too. Stellar average densities on the main sequence, I should say. Decrease as we move towards earlier spectral types. So we should emphasize that, and that means we're going from M towards O in terms of mass on the main sequence. Are we going from higher masses to lower, or from lower masses to higher? Going from M to O on the main sequence, what's that doing with mass? There's a mass-luminosity relation. So those O-type stars, are they high mass stars on the main sequence or low mass stars? Burn into brain. Going up the main sequence, is it the high mass or the low mass? The high mass stars, right, so burn into brain. The high mass stars are the early spectral types, the O's, the B's, those are the high mass stars. chugging their fuel and not living very long as a result, because even though they have higher masses, they chug their fuel a lot faster, right? Because the rate of fusion increases much quicker than the mass does as you move up the main sequence. M to O, low mass to high mass. All right, so that just needs to be second nature to you, that the higher up you are on the main sequence, the earlier the spectral type, the higher the mass of the star, but the shorter the lifetime of the star because it's burning its fuel so quickly. So the sun, anybody remember roughly what's the sun's main sequence lifetime? Approximately how long will the sun stay on the main sequence total? About
7 billion.
not too bad, not too bad. About roughly 10 billion years is what we would typically say. It's like 9 point something billion years, about 10 billion years. A very high mass O star might spend only 1 or 2 million years on the main sequence, right? And I say only, but I mean, you know, compared to a billion. Whereas a very low mass star could spend more than 1 trillion years on the main sequence, which is much older than the universe is. Probably worth saying this if you've never heard this before, so I'll fill that in later. Let's tell a story, right? Some of you might have heard me tell this story before, but it's a good illustration because when we hear billion, trillion, etc., it tends to just blur into, oh, it's just a zillion, it's just a big number, who knows, right? So suppose that I gave you $1 million and your job is to spend that $1 million at the rate of $1,000 a day. How many days does it take you to go through $1 million at the rate of $1,000 a day? How many days will that take? Well, in other words, 1 million is 1,000 times what? 1,000, right? Because 1 million's 10 to the 6, 1,000's 10 to the 3. So 1,000 times 1,000 is 1 million. So if I give you $1 million and you have the enviable job of spending it at the rate of $1,000 a day and you get to keep whatever you buy, how many days are you going to be spending that cash? 1,000 days, right? How many years is that roughly? Yeah, roughly 3. It works out to be like 2.6 because there's 365 days in a year. So that takes you about 2.6 years to spend $1 million at the rate of $1,000 a day. So now let's compare a billionaire to a millionaire. I give you $1 billion. How many times bigger is a billion than a million? 1,000, right? Because a billion's 10 to the 9, a million's 10 to the 6. So it doesn't take you 2.6 years to spend. So $1 million, you take 2.6 years to spend that at a rate of $1,000 a day. How many years does it take you to spend $1 billion? Compared to a million, how many times longer? A billion is how many times a million? 1,000. So how many times longer than 2.6 years will it take to spend $1 billion? 1,000 times. What's 1,000 times 2.6?
2,600.
About 2,600 years. So if you were given $1 billion and you had to spend it at the rate of $1,000 a day, it would take you about 2,600 years spending $1,000 every day to go through that pile of cash. That means that if you started 600 years before the year 1, you'd just around now be finishing spending that cash. Or if you started now, you'll be done in around the year 4,600 or something like that, right? $1 billion is fantastically larger amount of money than $1 million is. And so I'll let you decide what you think the socio-political implications of that ought to be. Leaving that aside, in terms of star lives, right, a star living 10 billion years is vastly longer than a star living 10 million years. And it's in that sense that I can say without batting an eye, oh, that star will only spend 10 million years on the main sequence because I'm comparing it to how long the sun would. That's only 1/1000th of how long the sun spends on the main sequence of 10 billion years. I mean, 10 million years is a long time by human standards. Here's another one, right? And I think it's worth having these kinds of things in your head, right? Don't confuse million and billion and trillion. They're very different things. So, how many millimeters are there in a meter? 1,000, right? Okay. So, how many centuries are there in a million years? A million years is 10 to the 6 years. A century is how many years? 100, 10 to the 2. So how many centuries in a million years? 10,000, yeah. So a million years is 10,000 centuries. So if you want to picture a million years, okay, step a millimeter, the smallest mark on this meter stick, wait 100 years, and when you're done, step to the next millimeter, wait 100 years, a century, and when you're done, step to the next millimeter. How far will you have traveled at that rate in a million years? If it's a millimeter per century, how long to travel a million years? It's as long as it takes to go the distance of 10,000 millimeters, because there's 10,000 centuries in a million years. 10,000 millimeters is how many meters? 10 meters, right? So a million years, how long is that? It's the time it would take to go from the front of this room to the back of the room, which is about 10 meters, at the rate of 1 millimeter per century. That's a million years. So what's a billion years? Well, now you got to go not 10 meters, but 10 kilometers at the rate of a millimeter per century. So a billion years, go 1 millimeter per century, and when you've gone 10 kilometers, 6 miles, you have elapsed a billion years. Why do that only 15 times, and that's the age of the universe, right? But again, I think, things like this are really good to think about, right? Because I can't picture how long a million years is or how long a billion years literally, right? But on the other hand, I can kind of get there by thinking, so can you picture how long a century is? Well, kind of, because you probably have reasonably clear memories about 10 years back. I can do better, but you can remember clearly about 10 years back. So you can kind of swallow 10 years. So think of that 10 times, that's a century, right? So you can kind of swallow a century. 10 times, as far as I can remember now, isn't incomprehensibly longer than you can remember now. And given that, you can sort of start to see what a million years is. You should think, okay, now I got to do that and get all the way to the back of the room, 1 millimeter every century. I still don't know what it means, but I kind of do as a result of thinking like that. And then a billion, and so on and so forth. And then also what's part of this is just realizing how many freaking times more a billion is than a million, right? People tend to just turn them all into a zillion. Million, billion, what's the difference? There's a huge freaking difference between a million and a billion. A star living 10 million years is tiny compared to a star living 10 billion years like the sun will, right? It's just not unbelievably long, but it's just way longer. It's just not the same thing. And that's why I don't bat an eye. I'm not at all being facetious when I say, well, that star is only going to live 10 million years. Well, that's like nothing, et cetera, et cetera. Yeah, so that was a long and winding detour, but I think a worthwhile detour. Be thinking of things like that, right? Be thinking of making scales in your head to try to comprehend the kind of numbers that we're dealing with in astronomy. Think of the dinosaurs. How long ago did the dinosaurs go extinct?
20 million.
It's more like 65 million years ago, about 65 million years ago. That's yesterday, because the Earth's 4.6 billion years old, right? So that's a lot more than 65 million years old. If you said, okay, we'll call it, okay, what's the exact number? Put it in your calculator. But 65 million 46 million, kind of the same. So 46 million versus 4.6 billion. 46 million times 10 is 460 million, times 10 is 4.6 billion. So when the dinosaurs died out, the Earth was like something like 99-ish% of its present age. It was practically yesterday that the dinosaurs went extinct. It was hardly any time at all ago. And yet we tend to think of it as really, really ancient history. Well, it is by human standards, but not that ancient, cosmically speaking. Those kinds of things are worth thinking about. That, right? And you might have heard the one before too, you know, on a more human time scale. Cleopatra existed closer in time to you and me than she did to when the pyramids were built, right? And we tend to compress ancient history, right? It's all just, oh, it's all happened at about the same time. The Romans thought the pyramids were ancient, and they were. The pyramids were older in the time of the Romans than the Romans were in the time of today, right? That's something to think about. The pyramids preceded the Roman Empire by like 3,500 years, and the Roman Empire was about 2,000 years ago. So the ancient history is a much longer span than we tend to make it in our heads, right? And universe history. It's a, you know, don't compress things. Be thinking actively about how things really compare to one another in time and so forth. So, what time is it? And now, let's do this, right? So, detour, but again, I think it's a worthwhile detour. I hope it inspires you to actually think about those kinds of things. It's one of my hobbies is to come up with things like that, right? So, and then if you're ever teaching, right, you throw those out at people, right? Because it's freaking cool. Anyway, sun. When you run the numbers, right, you find the sun's mass over its volume. The density of the sun would be on average, so it would be an average density rho bar. It varies from place to place. It would be the sun's mass divided by 4/3 pi sun's radius cubed. And what you get out of that is that it's about 1,410 kilograms per cubic meter. So what's, in terms of kilograms per cubic meter, what is the density of liquid water? Well, you learn in whatever grade that the density of water, let's see, 1 gram of water occupies about how much volume? Yeah, cubic centimeter. So 1 gram in a cubic centimeter, 1 gram per cubic centimeter. So a cubic meter is how many cubic centimeters, right? So if I take a cube, if I made a cube of water, 1 meter wide, 1 meter tall, 1 meter deep. So I could make a cubic meter of water here. How many cubic centimeters in a cubic meter? 1,000. Let's see, 1 centimeter is, well, how many centimeters in a meter? 100. So it's 100 times 100 times 100. So that's 1,000,000 cubic centimeters in a cubic meter, only off by a factor of 1,000, right? Yeah, womp womp. Que sera. So, you won't get that reference probably. 1,000,000 cubic centimeters in a cubic meter. So 1,000,000 grams would be the mass of water. It's not quite a gram per cubic centimeter with the more modern definitions, but a cubic meter, and it depends on temperature, blah, 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 but a cubic meter of water would have a mass of about 1,000,000 grams. How many kilograms is that? 1,000 kilograms, yeah. So the density of water is about 1,000 kilograms per cubic meter. A metric ton, so that's right, 2,200 pounds if you turn it into English units of weight. So a cubic meter of water has a mass of a metric ton, kind of like a car, essentially, right? So don't try to lift it, you'll hurt your back. So in other words, this is approximately, the sun's average density is about that of liquid water, which is 1,000 kilograms per cubic meter. The sun, okay, 1410 kilograms per cubic meter. Now, the core of the sun is denser than lead, quite a bit denser than lead. The outer layers of the sun are very, very tenuous, much less dense than Earth's atmosphere. It turns out 90% of the sun's mass is in the inner 50% of its radius. The outer layers are just kind of puffy compared to the inner part. But this is the overall average density of the sun. It's gaseous throughout. It's about as dense as liquid water. Well, now let's get serious. So its mass is about 2.2 times the sun's. Its radius is about 1.6 times the sun's. Put in the numbers and what do you get? That its average density over the sun's average density, rho bar over rho bar sun, would be, well, that would be the mass ratio, its mass divided by the sun's mass, times the cube of the reciprocal of the radius ratio, so r sun over r Sirius cubed, because we're dividing, and that works out to be about 0.54. So Sirius is about twice the mass of the sun, but only about half the average density, because it more than makes up an extra volume for the extra mass that it has. And then if we go off the main sequence to my second favorite star, what's my second favorite star? My second favorite, the one I go, blow up, every time I see it? Betelgeuse, Betelgeuse, yes, Betelgeuse, a delicious crushed insect beverage, Betelgeuse. Its mass is roughly about 10 solar masses. It's not a binary, so we can't measure it precisely. It's a pulsating variable with a maximum radius of about 1,000 times the sun's radius. If you put it in the solar system, sometimes it would eat Jupiter. It pulsates, which is why I say R max there. It pulsates. It's a pulsating variable star. It pulsates. That means that its density over the sun's density on average, it's about only 10 to the minus 8 as dense as the sun. About 1/100 millionth as dense as the sun for this M21A supergiant. That's its MK spectral class, M21A supergiant. So it's going to blow up good someday, but until then, boy, it's a big old puffball. So I think it's true that if you look at the sun, it seems to have a sharply defined surface. I've never seen this for sure. I should do a calculation or something, but a supergiant like that, if you were close to it, when you see illustrations, they make it kind of look like they have nice sharp surfaces too. But I think what you would actually see is just that it would just be fading to black in the outer layers. In other words, it wouldn't look like it has a sharp surface. It's just like bright, 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 less bright, less bright, ooh, dimmer, dimmer, ooh, it's just kind of fuzzy on the edges, and it just kind of fades away if you were looking at a star like that. Okay, we're done for today. And next time, we'll make use of those glorious packets and talk about binaries and all that kind of good stuff.